Hi! Within this lecture, we're gonna see a notation that we will be using intensely in order to simplify the mathematical formulations or mathematical operations that we will be working on for the following lectures. This notation is called Braket. So, of course, you can pronounce this like Braket, but it's actually Braket. And I'm gonna show you what it is. So, remember this. Okay, so we have taken the adjoint of the first matrix and then we multiplied it with the second matrix in order to get the probability. So we're gonna do this a lot, and also we're gonna actually represent the vectors or the column matrices a lot as well. So in order to simplify this, so Dirac came up with this bracket notation in which he actually simplified these operations in a much better way. So what happens over here is that you can see this angular signs over there, like this is called bra. Okay, the first one is called bra and the second one is called cat. So if you see this smaller than or bigger than sign with a piping sign in the middle or at the beginning or at the end, you know that you're dealing with a bracket notation. Okay, so if you see this bracket together, so like this, it means that we're gonna take the adjoint of the A and multiply it with the E. But if you see this cat only, okay, this one or that one, they represent some specific column matrices, okay, some vectors. So in this case, for example, if you see cat 0, it means that we are talking about the state 0, which is 1, 0. And if you see cat 1, it means that we're talking about the vector, which is 0, 1. So we know that it represents 1, 0 over here and the other way around at the left hand side. So the values over here like 0 and 1 doesn't mean actually anything. We could have just called them 0, okay, by writing by text, or 1. So we don't actually perform some kind of mathematical operations inside of this value. It's just a notation. So cat 1, when you see cat 1, know that we're talking about this particular matrix, which is 0 and 1. And if you see cat 0, then we're talking about the other matrix. And we need this because we're not only going to be dealing with one single qubit all the time, we're gonna deal with multiple qubits and it's gonna get ugly. So we're gonna have to know about this notation and leverage it in a way that it simplifies our operations. So let me go back here. So again, this is Circuit Composer. We're gonna take a look at it in like a couple of lectures, but know that we're going to be dealing with this a lot. And in the previous lecture, we have seen that notation. As you can see, this is cat 0 and it represents the 0 state over here. Okay, so this is like a visualization of the vector that we are talking about. And remember, I applied something called NOT gate to make it into one state. And over here, we don't see the matrix itself, we see the cat 1. But we know that it's talking about that particular matrix that we have learned about. Right, so over here we see that we get 100% probability of getting 1. So far so good. Now you have to understand that this is just a notation, okay? It's not a big deal. It's a way to simplify the matrices that we will be working on, but it actually helps us a lot. Most of the time, we're not gonna even see the bracket notation. We're going to be working with the cat notation, but let's see how it actually simplifies things for us. For example, we talked about this is a superposition matrix because 1 over square root 2, 1 over square root 2, if you just take the 1 over square root 2 as a coefficient from here, like a scalar, then you can actually simplify this like that, right? So what does it mean? It means that we get to actually take the 1 over square root 2 to the left hand side, and we can just simplify this notation by writing cat0 plus cat1. And believe it or not, we're gonna see this like 1,000 times more for the following lectures as well. So as you can see, it's easier to write this rather than writing the whole matrix, even in 1 qubit states. Okay, we are dealing with only 1 qubit right now. As you might remember, this is the probability of getting 1 or 0 for only 1 qubit. And by using this cat notation, we can actually specify the 2 qubit notations, 2 qubit states as well. So if we're dealing with multi-qubits or 2 qubits in the specific example, we know that we don't only have 1 or 0. We can have 0, 0 state, or 0, 1 state, 1, 0 state, and 1, 1 state as well. Right? So obviously in the qubit, during the quantum computations, it can be anything, not only 1 and 0 as we talked about, but once we eventually measure this, it will collapse into 0 or 1 for the classical qubits, in order for us to understand what's going on. And then we need to specify the states in cat notations, and it would be much more easier for us to do that rather than just writing whole matrix. So this matrix over here represents the cat 0, 0, and this one cat 0, 1, cat 1, 0, and cat 1, 1. So how do we actually build these matrices? Okay, maybe we have understood that the cat 1 is this. Okay, so cat 1 is 0, 1, and cat 0 is 1, 0. But how do we go from there to here, cat 0, 0? It's very easy actually. Once you deal with multi-qubits, you're gonna have to introduce the tensor products that we have seen before. So for cat 1, 1, you're gonna have to take the tensor products of 0 and 1, and you're gonna see it will add up to this. And it's all the same for all the column matrices, the vectors that you see over there. For exercise, I really suggest for you guys to stop the video, pause the video, and try to calculate the tensor product of cat 0 and cat 0 together. Let's see if you can get this particular matrix that we are seeing right now for cat 0, 0. Of course, in time, whether you deal this exercise or not, you will get used to the fact that this is the cat 0, 0, this is the cat 0, 1, and cat 1, 1, and so on. You will immediately know what this is once you see it, but this is since this is the first time that you are seeing it, maybe it's a little bit foreign to you, it's a little bit out of ordinary, so I really suggest you pause the video, try this on your own, and see for yourselves. And we're gonna stop here, so I really suggest doing that exercise before coming into the next lecture, and then meet me within the next lecture.